Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers the first part of section 1.1 on vector equations. I'll teach you all about the 7 topics listed here, and by the end of this video, you'll have a much better understanding of vectors and their use in linear algebra. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's start by learning what Euclidean space is. Euclidean space is the fundamental space of geometry, and it's intended to represent physical space. There are 6 key characteristics of Euclidean space that we'll be talking about in this course, and we'll talk about 3 of them now, and then 3 of them later on in the course. The first key characteristic is dimensions. The symbol R and the letter N are used to describe Euclidean space. R is the set of all real numbers, and that's all the numbers that can be found on a number line, and N is the dimension of the space. Because R is the set of all real numbers, it's called one-dimensional Euclidean space, and it's just the real line shown here. We'll label the line with coordinates x or x1. R2 is two-dimensional Euclidean space and is a plane. We'll label the plane with coordinates x or x1 and y or x2, and we'll call it the xy plane or the x1, x2 plane. R3 is three-dimensional Euclidean space, and it's just the space that we live in. We'll label this space with coordinates x or x1, y or x2, and then z or x3. Rn is Euclidean n-space. Euclidean n-space serves as a foundation for analyzing and solving problems in various fields, especially those involving multidimensional systems. Another key characteristic of Euclidean space is coordinates. Points in Euclidean space are defined by coordinates, which are just ordered sets of real numbers. In this course, we'll be writing a point in R2 as xy or x1, x2. We'll write a point in R3 as xyz or x1, x2, x3. And then we'll write a point in Rn as x1, x2, all the way up through xn. We'll see later in this course that there's many applications that utilize points in Rn. The other 4 key characteristics of Euclidean space are distance, vectors, angles and orthogonality, and then vector spaces and subspaces. We'll learn about vectors now, and then we'll learn about the other 3 key characteristics later. We'll start learning about vectors by first learning about vectors in R2. In general, vectors in Euclidean space are mathematical objects that have both magnitude and direction, and they're defined by components. All vectors in Euclidean space have an initial point, which is often referred to as the tail of the vector, and a terminal point known as the head or tip of the vector. As I mentioned above, vectors are defined by components. A vector in R2 can be written in terms of its components v1 and v2. We can write v like this. We have v is equal to v1 and v2. v1 is the first component of v, and v2 is called the second component of v. Our vector v is a 2x1 column matrix because it has 2 components. It's called a column vector because it has a matrix with 1 column. Using the Pythagorean theorem, we can write the magnitude or length of a vector as the square root of its components squared and added together. Two vectors are called equal if they have the same magnitude and direction and they have the same initial and terminal points. In our diagram here, u and v will be equal if u1 is equal to v1 and u2 is equal to v2. Two vectors are equivalent if they have the same magnitude and direction. They don't need to have the same initial and terminal points. In our diagram, vector u has components u1 and u2, and it's equal to 2, 2. Vector v is the vector between points P and Q and has components v1 and v2. v1 is equal to 5 minus 3, and v2 is equal to 3 minus 1, giving us the components 2, 2. Because the components of u and v are equal, the vectors will have the same magnitude and direction and are called equivalent vectors. Let's now see what happens when we multiply a vector by a constant. When we look at this GeoGebra link, we can visualize how a vector changes when we multiply it by a scalar. I've placed this link in the video description below. When we multiply a vector by 1, it stays the same. When we multiply a vector by a constant greater than 1, it lengthens. When we multiply a vector by a constant between 0 and 1, it shortens. And then, if we multiply a vector by a constant less than 0, it reverses its direction. Let's now look at an example where we're given a vector u and asked to compute 3u and then minus 2u. 3u is going to be 3 times our vector 6, 2. When we multiply a scalar times a vector, we have to multiply that scalar by each component in the vector. So 3 times 6 is 18, and then 3 times 2 is 6. Multiplying vector u by 3 triples the length of the vector. Let's now compute minus 2 times u. This is equal to minus 2 times our vector 6, 2, and we get the vector minus 12, minus 4. Multiplying our vector u by minus 2 doubles the length, but then reverses the direction. We'll now look at how to add and subtract vectors and then visualize this using GeoGebra. When we add two vectors algebraically, we just add the corresponding components. U plus v is going to equal u1 plus v1, and then our second component will be u2 plus v2. We can use GeoGebra to see how to add two vectors graphically, and to do this, we'll use the parallelogram rule for addition. We'll start with two vectors whose initial points are at the same point. We then construct a parallelogram using the vectors as adjacent sides. The diagonal of the parallelogram represents the sum of the two vectors. When you get done watching this video, be sure to check out the GeoGebra link in the video description below so that you can explore and experiment with it and see how it works. To subtract two vectors algebraically, we just subtract their corresponding components. U minus v is going to be u1 minus v1, and then u2 minus v2. We can use the parallelogram rule of addition to subtract two vectors graphically if we write u minus v as u plus minus v. Let's look at GeoGebra again and see how that works. Just like with vector addition, we start with two vectors whose initial points are the same point. We then plot minus v and construct a parallelogram using u and minus v as adjacent sides. The diagonal of this parallelogram then represents u minus v, or the difference between u and v. Let's now look at an example where we're given u and v and we're asked to compute u minus 2v. U minus 2v is going to be our u vector, 2, 3, minus 2 times our v vector, 1, 4. This gives us a vector with components 0 and then minus 5. Vectors in R3 are 3 by 1 column matrices, or column vectors with 3 components. We can write our vector u in R3 as u1, u2, and u3. Let's now look at an example and see how to draw this u in R3. We'll start by moving 2 units in the x1 direction. We'll then move minus 1 in the x2 direction, and then lastly, we'll move up 3 units in the x3 direction. We can then draw our vector u. Let's now talk about vectors in Rn. Vectors in Rn can be viewed as a collection of all lists of n real numbers, and we often call this ordered n tuples. We'll write vectors in Rn as n by 1 column matrices, which are just column vectors with n components. Our u looks like this. It has components u1, u2, all the way down to un. Let's now briefly go over the algebraic properties of Rn. We're going to assume that u, v, and w are vectors in Rn, and c and d are scalars. The commutativity property tells us that we can change the order in which we add the vectors. The associativity property tells us that we can change the order in which we add 3 vectors. We can add the first 2 together and then the third, or we can add the second and third together and then add the first. The additive identity property tells us that when we add 0 to a vector, we get back that same vector. The additive inverse property tells us that adding the inverse to a vector gives us the 0 vector. The distributivity property of scalar multiplication over addition tells us that we can distribute a scalar and multiply it by both vectors. The distributivity property of scalar addition over scalar multiplication tells us that we can multiply the addition of 2 scalars times a vector by multiplying each scalar times that vector separately. The associativity property of scalar multiplication tells us that we can multiply a scalar times a vector separately, or we can multiply it together. Lastly, our multiplicative identity tells us that when we multiply a vector by 1, we get back that same vector. Let's now learn about a very important and fundamental concept in linear algebra called linear combinations. Vectors v1 up through vp are vectors in Rn, and c1 up through cp are scalars or weights. The linear combination of v1 up through vp with weights c1 up through cp can be written as y is equal to c1 v1 plus c2 v2 all the way up through cp vp. This equation will have a solution for c1, c2, all the way up through cp if y is a linear combination of the v's. We'll use GeoGebra to visualize what a linear combination of 2 vectors looks like. We begin with a blue vector v1 and a pink vector v2. We're going to multiply v1 by c1 and v2 by c2. In the slider, we can change the values of C1 and C2. Using the parallelogram rule of addition, the green vector is the linear combination of V1 and V2. In the previous page, we saw that a linear combination of vectors V1 up through Vp can be written like this. This equation is called a vector equation. It's an equation that involves vectors, and it's used to represent lines, planes, and more general geometric entities in space. A linear system of equations can also be represented by a vector equation. We're going to learn in the example below how to write a linear system of equations as a vector equation that looks like this. In this example, we're going to write the linear system as an augmented matrix and then as a vector equation. We're starting with an augmented matrix because we already know how to do that. Our augmented matrix is going to look like this. We have the coefficients multiplying our x1s, and then the coefficients multiplying our x2s, and then the coefficients multiplying our x3s. And then we have our line and our right-hand side. We're going to call the columns of our augmented matrix A1, A2, and A3, and we're going to call the right-hand side as B. We can then write this augmented matrix as A1, A2, A3, augmented with vector B. To write our linear system as a vector equation, we're going to multiply x1 by the column vector that contains the coefficients multiplying x1. That's 1, minus 2, 0. We'll then add x2 times the column vector that contains the coefficients multiplying x2, and that's 0, 1, 2. And then we have x3 times the vector 5, minus 6, 8. And that's all equal to our right-hand side, 2, minus 1, 6. In general, this is going to be written as x1a1 plus x2a2 plus x3a3 is equal to b. In practice, if we're given the vector equation x1a1 plus x2a2 plus x3a3 is equal to b, and we want to see if b is a linear combination of a1, a2, and a3, what we have to do is write our linear system as an augmented matrix and put it in echelon form. If it has no solution, then we know that b is not a linear combination of a1, a2, and a3. If it has a solution, either one or infinitely many solutions, then we'll know that b is a linear combination of a1, a2, and a3. If we go on and reduce this matrix to reduced echelon form, we'll get the weights x1, x2, and x3. Let's look at those above. That's these terms. And they will tell us exactly how B is a linear combination of A1, A2, and A3. Let's do some examples so we can really understand how this works. We're asked to determine if B can be written as a linear combination of A1 and A2. We'll start by writing down our augmented matrix, 1, 3, 2, 6, and then 4, 6. Our matrix in echelon form looks like this. On the top, we have 1, 2, and 4, and on the second row, we have 0, 0, minus 6. When our left-hand side is equal to 0 and our right-hand side is a non-zero number, we know that we have no solution. This tells us that B cannot be written as a linear combination of A1 and A2. Geometrically, we can see that A1 and A2 lie along the same line, and B does not lie along that same line, so it can't be a linear combination of A1 and A2. Let's now look at our second example. Just like the first one, we're going to create our augmented matrix. And then we're going to put that augmented matrix in echelon form. We get a matrix that looks like this. We have a pivot in every column, and that tells us that we have a unique solution. That means that B can be written as a linear combination of A1 and A2. To see exactly how we can write it as a linear combination, what we're going to do is we're going to take our matrix in echelon form and put it in reduced echelon form. That matrix looks like this. We can see that x1 is going to be 7/3 and x2 is going to be 4/3. So we can write B as a linear combination of A1 and A2 like this. 7/3 A1 plus 4/3 A2. Let's do one more example. We'll put our vectors in an augmented matrix. And then we'll put that matrix in echelon form. Our matrix in echelon form looks like this. And you can see, because we have a row of zeros equal to 0, and our second column missing a pivot, that we're going to get infinitely many solutions. Let's write that down. To see what our solutions look like, let's put this matrix in reduced echelon form. We get the matrix 1 minus 1/2 and then 1/4 with zeros on the bottom. This tells us that x1 is equal to 1/4 plus 1/2 x2. x2 can then be any number. If we pick x2 to be equal to 1, we would get the solution 3/4 1, which would tell us that B is equal to 3/4 A1 plus A2. Since we have infinitely many solutions, we'll have infinitely many ways that we can write B as a linear combination of A1 and A2. Let's now look at some application problems that utilize linear combinations of vectors. The RGB color model is a system for representing colors using the three primary colors red, green, and blue. Red is written as 1, 0, 0. Green is written as 0, 1, 0, and then blue is written as 0, 0, 1. A color can be written as a linear combination of these three vectors. As an example, we could let K1 be equal to 1, K2 be equal to 1, and K3 be equal to 0. That color then becomes 1, 1, 0, and that's actually the color yellow. In our second example, we'll use linear combinations of vectors to calculate the center of mass of a thin triangular plate. Our thin triangular plate has uniform density and thickness and has vertices 0, 1, 8, 1, and 2, 4. To find the center of mass of the plate, we'll use the formulas V bar is 1 over m times m1 v1 plus m2 v2 plus m3 v3. Our m is equal to m1 plus m2 plus m3, and they're the point masses added at the vertices of the plate. V bar is a linear combination of the vertices locations divided by the mass of the plate. You may have also seen formulas for the center of mass written like this. The center of mass is just a point that represents the average position of all the masses in a system or object. It's the point where you consider the entire mass to be concentrated. Since we have 1 gram point masses added at the 3 vertices, our m is going to be m1 plus m2 plus m3. And that's going to equal 1 plus 1 plus 1, which is 3. Our V bar then is equal to 1/3 V1 plus V2 plus V3. This is equal to 1/3 times 0, 1 plus 8, 1 plus 2, 4. And this is all equal to 10/3 and 2. This is the location of the center of mass of our plate, which we can see in our diagram is right up there. Be sure to check out the next video in this series where we'll learn all about linear independence.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.